to this lab. Kind of like the most reverse engineering we'll be doing in this class. Like I said, I didn't want to make reverse engineering a prerequisite for this class, but invariably when you're doing Windows exploit development, you're going to have to do some reverse engineering to figure out why the program is crashing, where it's crashing, what it's trying to do, just at the point where your exploit is trying to run. It'll also come in handy when we're analyzing crash dumps to see if they're exploitable or not, just to have, a little bit of reverse engineering chops. But in case the term reverse engineering scares you, if you have no experience with this, you can just relabel it debugging. That's what we're really just doing, is using our debugger to try to figure out what's going on. So let me see, I'll fire this thing up in a debug session. If I was doing this, what I would be thinking about, if I had no prior knowledge of all this program was doing. So looking at this, what do we think the first few lines of the program are doing? We see like push EBP, move EBP, ASP, which is like
Corey, can you make the text big again?
log, right? Oh yeah.
Yep.
Better? So looking at this, guys, this is the very beginning of the main function for mystery, which is the first few x86 instructions to execute. What do we have a general idea of what's happening here? In fact, before we even try to speculate about higher level reasoning about what it's doing, let's just try to step through it, get a feel for what's happening. So I'm just going to single step, see what happens. Okay, here it's comparing a value. And then if it's equal, it's going to jump somewhere. Otherwise, it's going to do something else. Whenever I see something like this, when I'm reversing something and I see a value, okay, what is it comparing? Just looking at that, does anyone know what that is? What? Yeah, right ballpark. Can you tell me exactly what argument it is? So everything below EBP is like a local stack variable, and above EBP, generally in x86, is a argument to the function. So Sam is right. EBP plus 8 in this case is argc, which is the number of command line arguments passed to the program. Assuming I didn't know that, I would just want to check out what that is. It's 1. Okay. If I didn't know it was argc, I would, okay, that's 1. Just make a note of that. T 1 is not equal to 3, so we're not going to take that jump. It's pushing something on the stack. I was going to call printf. And I want to see what it just pushed onto the stack, which I know is what it's going to printf. And what I did here was the DA command, which is described as an ASCII string, So like look at this pointer and try to display this string. So what this is going to do is it's going to print this message that we've been seeing on the command line. It's okay, Maybe or maybe not vulnerable code follows after that. But let's just see where the program goes. Oops. Didn't want to step into the printf function, not interested in that. Screwed up my Okay, so we call it printf, and it's cleaning up the stack. Looks like it's setting a return value, jumping somewhere. They're just leaving the main function. So the way it's executing right now, it's not doing anything. It's just printing a message and then exiting. So there's no vulnerability there. So that was like a binary decision binary branch we took there. Either to compare EBP plus 8, either jump or don't jump. At this point, we executed this, so obviously that isn't doing anything interesting, so we want EBP plus 8 to be equal to whatever it was comparing against, 3. So for it to do anything interesting, to expand our code coverage, we have to make that compare evaluate true. So there's a hint number 1 for you guys. All the suffering, the pain train continued for a while. Based on this code, if the compare evaluates true, looks like we'll call this function, whatever it is, mystery function plus something. So I would want to look in this function and see what's going on there. Those of you that did the bomb lab like 10,000 times should be going through this, right? So while you guys are working on this, I just want to bring up a high-level point. We can see right here that one thing we already had to deal with was we were comparing this value, EBP plus 8 to 3, and then if this compare didn't work out, we basically exited immediately. If we were developing a vulnerability and we discovered that, or we were developing an exploit for a vulnerability, we discovered that EBP was some value that we controlled. EBP plus 8, let's assume it's like EBP minus something and it's a local stack variable that we're approaching with our payload. We would know that, okay, well, if this compare doesn't check out, then the function is kind of exit, and we're never going to actually do that vulnerability and corrupt the process. So I have to make sure that that is that this particular part of my payload is 3. That way the process continues execution. And you always have to keep in mind these kind of constraints that are going to be placed on your payload. Like whatever part of my payload is overriding this has to be equal to 3. And in general, when we're reversing or fuzzing, we want to increase what's called code coverage. So in this case, if EBP plus 8 is not equal to 3, our code coverage is very poor. That's just going to fail this compare and print a message and exit out completely. And the more code that executes, the more potential bugs or vulnerabilities you're going to step over. So you just want more code to execute. So for instance, in this case, I'm going to sort of draw like a IDA Pro kind of block diagram that represents a program. This is something I'll talk about again when we're talking about fuzzing. But let's say this is our entry point into main, or in general, any type of program that we're trying to exploit. And right here, it's doing the compare. I'm just going to say argc because that's what it is. Can the remote people read this okay?
If Bill, could you zoom in a little bit on that? That's good, thanks.
Yeah, that's good. So in this case, we have like this IDAPRO block diagram and this compare argc. And if the compare argc fails, we're going to take this, which is basically just, exit program. So right now, if argc is not 3, we're just taking this path. But when we're fuzzing, we want to explore as many paths as possible because the more code you step over, the more code you look at, the more code you touch, the more bugs you're going to hit. So if there's a bug down here in this IDAPRO block, and over here in this one, we would never be seeing them because that compare doesn't work out. It just exit immediately. So when we're fuzzing, for instance, we want to be aware of this, that if this value isn't equal to this, we're just going to exit it immediately. And we want to make sure that we're hitting all the constraints properly, we're generating constraints properly so that we end up iterating over these blocks and executing these blocks as well. So eventually we'll hit these vulnerable blocks of code that contain vulnerable calls like calls to sprintf or string copy or memcopy or scanf and hopefully get a crash. So talk about this again in the context of fuzzing later on, but in general, vulnerability discovery, exploit development, you have to figure out what these constraints are on your payload and your data and figure out how to best expand code coverage so you can hopefully hit these vulnerable blocks. So in this case, if args equals 3, we're going to do this branch, and then hopefully something good will happen as we continue execution down this branch in the mystery program. So I'll just sort of work through this a little bit more, try to step through the process for anyone that's confused at this point. So, okay, I know that argc has to be 3, which means I need to pass it 2 additional arguments, right? It's kind of the weird little gotcha there. Let's step again. Okay, so I hit the jump this time. I'm excited. We're executing code that we have never executed before. We're on the new frontier, hopefully one full of strange people and awesome vulnerabilities. And okay, we're going to call this function. And since I've not been in it before, I definitely want to step into it. So I'm going to do T for step into. And jump through some like relocation tables here. Nothing too interesting. Okay, we're just executing a function. So, when I'm looking for vulnerabilities, whenever I see subtracting like a large amount out of ESP, that usually kind of spikes my curiosity because this usually means that they're doing a lot of stuff with local variables. Whenever there's a lot of local variables flying around, that often means there might be a vulnerability there. So I'm like, okay, well, this function might be worth looking at. Another important part of reversing I want to say is that knowing like what not to worry about or what not to analyze is like equally as important as knowing what to analyze. So if this function was just like 5 instructions here and then returned, I would like, I don't even want to waste my time on this. I'm just going to step out of this and then make a note that mystery function or whatever the address of the function is at isn't worth my time. Not interesting, so that whenever I see that function be called again, I know just to step over it and not even bother stepping into it. But in this case, got a lot of stack variables getting allocated, stuff going on. So yeah, okay, I'll take a look at this thing. Okay, so all right, setting some local variable equal to 0. Another local variable equal to 0. Jumping somewhere. Okay, well we got to take that jump, so I may as well step into the jump. Okay. Another compare. I'm thinking as an attacker, is EVP minus 4 something that I control? We know right away that we might not know this. We might have to inspect it and sort of reason about whether or not it's something that we control. In this case, we know that it's not because we see right up here that EVP minus 4 is initialized to 0. So, okay. Interesting. So we know that this compares, on a fail, jump greater than or equal to. So 0 is less than 80 in X, so we're not going to take that jump.
I'm assuming that this is a loop of some kind.
Yeah, exactly. Move ECX, EBP minus 4, so I'm just going to go ahead and assume when I see EBP minus 4 that's like I, or iterator, type of like iterator value, okay, whatever. All right, I don't know what's going on here. It's like moving some data somewhere. Okay, one thing that's I'm making note of mentally here when I'm looking at this is that none of this so far seems to be operating on my data. So at this point, the only data of ours that's entered into the program apparently is those command line arguments. We know that it's comparing to make sure that we have 2 additional command line arguments. But I know it's not using any of those because it's doing like looking at stack variables. I don't see any like EVP plus 4 or 8 or whatever. This is doing EVP plus, but immediately minus 490. So it's probably indexing off some array, what I would guess here. So, okay, so this loop doesn't appear to be touching our data so far. All right, it's like moving a byte value, doing something. Still not touching our data, it's still just messing with these local variables that we have no control over. Okay, now it's adding 1 to our iterator. It's kind of like go through this loop again. So what I would do if I'm trying to exploit this program is I would think, all right, we have a loop here. It looks like the only exit out of this loop is this jump greater than or equal. So the only way this loop is ever going to exit is when the iterator equals 80. It looks like that's just being monotonically increased. So, okay, I just have like a simple loop here. It's not even like touching any of my data. And I know that eventually it's just going to exit and then continue execution of the function. So what I would do is I would say, I don't even care about this loop because it's not operating on my data. As an exploit developer, we really only care about, or we generally only care about the functions that are operating on our data, operating what's known as the tainted data, sources of attacker input, because those are the things we can control and try to leverage to corrupt the program. In this case, we don't control really any of the components of this loop or any of the components in this block of code, so yeah, so Sam asked, did this function even have any parameters? Well, you can answer that. How would you answer that question? x86. You would look at the call, see if anything was pushed onto the stack before the call. At this point, it looks like the only tainted attacker data that's even entered into the program has been those 2 command line arguments. And they weren't even seemingly passed to this function, so it looks like at this point, our data, any attacker-controlled data, isn't even influencing the process at all. So I really don't even care about this stuff right now. So what I would do is, okay, oops. Where does this function end? All right, compare jump greater than or equal to, where am I going to? 401072. All right, right here. I can just do run the cursor. So I'm like, okay, that loop was not interesting. It was like looking at some local variables that I don't control, looping over them and exiting the loop deterministically. So get past it, keep reversing, that will be my thought process. Just remember, when you're looking for these bugs, trying to develop exploits, you're really only interested in focusing on the code that is operating on your attacker-controlled data or influencing it in some way. Aha! The scepter of power. So I want to take a class poll and see what you guys want to do about lunch. What time is everyone feeling like for lunch?
I think it should depend basically on where you're at with the labs at the time. Ideally, you want to stop when you've got a lab.
So what I did in in McLean was that I think I stopped around like 11:15, and I just said that we were going to continue working on this lab over lunch, so that people were welcome to keep working on this over lunch.
Yep,
They
that
wanted
seems
to.
good.
So, um, yeah, okay. So we'll aim for around like 11:15 for like a 1-hour lunch, but I want to get you guys to the next step at least before I cut you guys loose for that. Also, Sam, if you use DC, I think even DB will tell you, but DC will tell you like the bytes as well as like their ASCII representation, as will DB. Yeah, I think it's all. So. And I think even DU will describe it as like a Unicode string or something. Yeah. I don't think we. I take that back. We might touch Unicode in this class, so it's another one to keep in your bag of tricks. So after this lab is over, we'll kind of officially finish the review part and transition part of the class, where you take what you know from exploits 1 and figure out how to apply it to exploits 2. And then we'll start talking about some Windows-specific topics that will be new to you guys, like exception handler overrides. We'll talk about today. And that'll be another target that we override on the stack besides the return address, which is actually generally a better target in Windows. For anyone racing ahead in the lab, the ultimate goal is to get the calculator shellcode to execute. So if you're way ahead of where I'm at in my walkthrough here, please continue in that direction. So what I would do here, let's continue my walkthrough. If you want to continue at your own pace, please close your ears and avert your eyes. Like, okay, I see a fopen call coming up. I know I'm going to execute it because there's no branching instructions between where I'm at and where it is. So, okay, let's see what it's trying to open. All right, so two things pushed onto the stack. So it's trying to 2 arguments for the fopen call. I'll do a DB first argument. Okay. So the first argument appears to be the string C:/hello there.bin and all terminated. So it's trying to open a hard-coded file. And this looks like this path is probably just hard-coded program because it wasn't passed as an argument into the function. We can see it's even coming from like a static region of memory, so it's probably some like a hard-coded constant. And there's another argument pushed on there, which I know is just the mode you want to open the file in. So R, here's it. So it's opening a file for reading. It's hard-coded. Let's see what's, okay, it's trying to open hello there.bin, which doesn't even appear to exist, so, all right, let's see what happens. Step over the call to fopen and we'll look at it. Okay, at this context, at this point in the program's execution, what does EAX signify? The return code for the function. So, all right, 0. And what I could do if I had access to the internet is I could look up the fopen function call and see what the return code is supposed to be. Now I would see that in this case, 0 null indicates like a failed value, failed, no good, failed to open, which isn't surprising since the file isn't even there. So it's going to compare the return value to 0. It's not going to take this jump. And one useful thing about WinDebug is it's telling you right here that the branch will not be taken, branch equals 0. So, okay, it's going to do a printf call. Not this damn message again. Oops. That's exactly. What's it called? Mystery function? Is that right? Okay, so yeah, it's going to call printf. Prints out this message again, this annoying message, and I want to see what else it does. So step over printf. see if you can jump unconditionally and then just exit. So once again, this doesn't do anything interesting. In this case, it's doing something like Bill, can I get the board here on the screen for a second? So assuming this is like kind of a block diagram for what mystery is doing. Here, we'll say that this calls mystery functions. So I'll move out of the way in a second for those of you that can't see. So if hello there.bin doesn't exist, it just returns immediately, and then it's going to go back up and just exit immediately, basically, so not too interesting. So we know for sure that we want hello there.bin to exist. So what I'll do is I'll just okay. Create a hello.there.bin file. Step past the loop. Let's jump right to this fopen call, actually. Step over fopen. Okay, this time EAX is a non-null value, so fopen succeeded, obviously, since I just created the file. All right, so now we're in the new territory. This is the code we're going to execute.
Hey Corey, can you step up to the fread and like show what's on your stack? Because mine is erroring out in the fread itself. Actually, it's like getting an access violation, but the parameters look fine to me.
Yeah. So you know what you're doing is you're putting so much data into the file that you're writing past the bounds of the stack. And
No, I
getting
checked it. So I confirmed that it's like the register values in the, there's like a rep move S that it's hitting, and the EDI and ESI are messed up kind of thing. So I had tried with too little and I had tried with too much, but it's either way it's erroring out in the inside fread.
Okay.
So I just want to see what the values are on your stack to make sure they're the same thing as mine.
Yeah. And so what I'll do is I'll try to step over the call too and see if I get an error. The error you're seeing. So what I've found, sometimes is that sometimes updating the file in HXD or whatever, if you do like a dot restart, it'll still like use the old file for whatever reason. So you might have to like restart Windybug, or just look with like a dd command on that. I guess yeah, it'd be hard to tell. If you keep track of where your buffer is located on the stack, at the time where the FREAD crashes, you can look at that buffer again to make sure it contains your new, updated, smaller payload. Because what I suspect is happening is that when you do the restart, it still reused the old file that was too big.
Yeah, I wasn't actually doing that restart. I was closing Windowbug between each one, so that's fine.
Oh, really?
I'll maybe it was that it was too big, and I'll cut it back down to the size I think it should be. But I kicked it up to the hex 800-ish, but we'll see.
Yeah. So so as you see here, it sounded like the same vulnerability. You saw it's going to do an fread call. The hello there.bin file is a file that we can create and control. So it contains our data. We're calling fread. Fread is reading in, it's 800 bytes. But the buffer is at most 408 bytes. And I can tell that just because EV is setting EBP minus 408. And once it gets to EBP minus 0, it's going to be overriding a safe frame pointer. So after 408 bytes, we're going to be overriding good stuff like the safe frame pointer and the return address. But here's the gotcha that I want you guys to be aware of. You should only write enough to overwrite the return address, because if you write too much past that, you're going to crash the program. The reason being, fread will continue to try to read in data and write it to the stack, and eventually it will be trying to write data past the boundaries of the stack, and that it will just crash when it tries to do that before it even uses that corrupt return address.
So Corey, that was one of my theories on my bug, but if you go to that EBP minus 408 address that you do, and you do so basically do like a DD EBP minus 408 plus 800, and that still seemed to be a valid address. It wasn't like that it was off the end of the stack. Right? See, it's still within range. I mean, it's possible that I suppose it could be, yeah, actually that may be what it is. It's off the stack as far as Windows is concerned in terms of accessible area, right. But Windowbug can access it.
Yeah, and it could be writing into like a non-writable region or something like that.
Yeah, that's probably what it is.
Because generally what you'll see in this class is if you see stack addresses at 12FF70, that means the limits of your stack is going to be 130000. And as soon as it tries to write a value there, it's going to crash. See, if you use the bang address command, Zeno, on 1300, you'll see as soon as you get to 1300, it's read-only.
Yep, that's what it was then. So I was just checking with that, and I should have just cut it back.
So remember, we're all about science and precision here. We want to overwrite the return address explicitly and nothing afterwards. In general, when you're developing an exploit, you want to corrupt as little of the process as necessary, because you want the process to live long enough to execute your payload. If you go and just destroy a whole bunch of stuff on the stack, it's possible that you will cause the application to crash before it even gets to the point where you control EIP, you can execute your shell code. So you always want to aim for the minimal corruption necessary. After lunch is over, we will focus on writing past the return address and overwriting other juicy things up further on the stack. Veronica just made a suggestion that Bing Ted one, yeah, will tell you that basically what it's saying is 1300 with the stack rolling down. As soon as you're writing above 1300, you're kind of like off the limits of the stack, and you're going to get that upsetting. So what I'm going to do now, guys, is we can break for lunch. You guys should hopefully know how to get to the point in the mystery program's execution where it's reading in attacker data, getting to a vulnerability. So I'm going to say we'll do lunch till 12:15, so you're free to go until then. We will continue working on this a little bit after we get back from lunch, because I want people to get calculators popping up on their computer on this one. And then once we are done with that, we'll talk about overriding exception handlers, which are stored above recurrent addresses on the stack, and actually provide kind of a juicier target for buffer overflows in the Windows environment. All right, so you guys feel free to take off or stay here and work, but we'll reconvene at 12:15.